Hello, gentle readers. Welcome to another episode of Moment in Motion. Today, February 9th, 2024. Well, last we left off reading from this book about the mathematics of medical imaging. So the mathematics of medical imaging basically involves that the medical imaging is the idea to have this sort of non-intrusive approach to find the inner visibility into some things. And so this is carried out in a usually sort of intrusive approach called X-ray imaging or gamma. We're using gamma rays or any of various particular sorts of the radiation that is sort of makes for that materials that are opaque otherwise can be have determined vis-a-vis the interactions with these waves, and their waves and interactions about moment and motion. With regards to that, then according to the theory, it's built up. What are the right sizes of things with regards to the intensity of these things, and with regards to the sensitivity of the collectors and detectors, and thus that with regards to the analog to digital and the sampling of these values, these measurements, and that it results possible to make for tomography. That this was the general idea that for something like radar and sonar and remote sensing has been discussed here, from reading from radar and sonar and from reading from waves and layered media. And similarly with this mathematics of medical imaging, that there's a lot of common factors that go into the theory and the formalisms that make it so that it's kind of well defined and well understood how to make use of all that follows from electron physics to arrive at that. Then it's possible to mathematically so to define a theory of these things and so on, carry it out. So there are a couple things I wanted to find corrections for since I've been reading some more and watching some of these videos. So one of them is that about the sum of the numbers from 1 to 100, and I said 51 times 50, but it's 101 times 50. This is the traditional story about somebody who figured out a way to find an addition formula and to work up a sum and or in this case a multiplication or product formula to make up a sum vis-a-vis the incredible power of exponents addition formula to compute products given a log table and these kinds of things, which are neat natural facts of mathematics. Then another thing I wanted to figure out a little bit more was reading from last time from the theory of mathematics and medical imaging. There is the idea of this L1 and L2 spaces. And so I was relating them to Lyapunov, but that's kind of has to do with Lyapunov and the exponent. So I really thought it had to do with Lindenmayer, L systems, that the L systems are a very, very flexible sort of approach to defining things parametrically in terms of like fractals and all a bunch of different things. That the Lindenmayer systems is a very general kind of thing. But really what it is Banach spaces. And then it's really about the convolutional setting, where convolution is an operation, addition is an operation, multiplication is an operation, exponent is an operation, tetration is an operation, convolution is an operation of sorts. And so it's kind of defined as about the operator calculus. And then also it reflects on these things that have to do with the orthogonal terms of what make for things like all these notions of the transforms that are so built this way, that the properties of the functions that combine in the middle of these regions of analysis, this windowing and boxing, to make up so for how the great effectiveness of the Fourier transform and Cohen-Mellon and Z and the wavelet transforms are not so dissimilar in terms of their form. If they kind of approach it from the corner, as it were, or from the origin. That these L1 and L2 spaces then are very particularly the settings for the convolutional setting. So I was curious to find a little bit more about what that is, because I don't really recall it, except that it was of great utility and simplicity and elegance to get that from a usual course in differential equations and the transforms, and then with regards to numerical methods. So following that, in usual sorts of approaches to reach a level of sufficient sophistication to arrive at tractable numerical methods, which is really par for the course for all kinds of things that kind of arise from finite element analysis and dynamical modeling and all that kind of stuff. So yeah, I wanted to know a little bit more about that, and that's what that's about. And so then we get into Banach spaces and Hilbert spaces, and I found some great little books that have to do with some lecture notes, and that these lecture notes kind of help it also get into some of the theory of what's called singular integrals. So this idea of the singular integrals is that singularities in the singularity theory are like division by zero. It's undefined. It's an indefinite quantity, not to number. Yet at the same time, in things like this hypergeometric setting where 0, 1, and infinity are the singular points, that it makes it so that they very, very much reflect things like the origin. There might not be division by zero, but it's right in the middle of all the numbers. It's also the multiplicative annihilator. It's also the additive identity. So it's just an example of something that in some contexts where the induction falls down, as for the divisibility of members of the complete ordered field, there's so necessarily another sort context to fill it out. As from the one side, the other side, working up this dialectic, working up the complementary duals, and working up these completions either way inaccessible to the other, yet both so existing, somehow meeting in the middle of nowhere, about how these are necessarily sorts of concepts to equip mathematics with enough of a context to arrive at how and why it is like so, and not missing out, as it were. So what I found were some of these lecture notes in mathematics. They're from Springer Verlag, Springer Press, and what they are, this is from Umberto Neri, and so it's issue 200 of this Department of Mathematics, University of Maryland, College Park, a collection of informal reports and seminars, singular integrals. And so here's the preface from it. Art, said Plato, is a copy of a copy. So are these notes. They form the content of a course. Because any introduction should be elementary, the only background needed by the reader is a knowledge of Lebesgue integration and some acquaintance with complex variable and the simplest concepts of functional analysis. So that's generally considered an upper undergraduate setting in mathematics. Here we call the complex analysis the Eulerian Gaussian complex analysis, because there are other ones. And here we call the functional analysis the function theory, because there are Cartesian functions and there are continuous functions. And here we talk about the space of these functions with regards to the Banach space and Hilbert space now. And with regards to the convolutional setting and in these functions, we talk about orthogonal functions and these families of functions and all these kind of things to do with the function theory. And then with regards to the integration, Lebesgue integration, or Lebesgue, there's, after Riemann integration, there's Lebesgue integration, and then there's Stieltjes. And so it's generally considered that this book was printed in 1967 or so, and copyright 1970, that then with regards to Stieltjes, that Stieltjes, Stieltjes, that after Riemann and Lebesgue, Stieltjes kind of brings them together. So Riemann is very familiar as the Riemann sums of vertical rectangles of vanishing width, and Lebesgue is vertical regions of vanishing height, and Stieltjes is like either or, kind of putting those together. Not to be confused with Jordan measure and Jordan content, and that those areas sum to make integrals, and not just as of counting terms, but of the differential analysis and the equations. That for moment and motion, I just wanted to reflect mostly upon that this book helps bring in more context of the singular integrals and the notion that any motion starts as of an impulse, but as all the higher orders of acceleration and these kinds of things, that it really reflects, besides the whole classical setting of all that brings us all that's available to the usual formulaic approaches and all that's the linear and the classical, that it really does have this linear to the nonlinear, the highly nonlinear, and the asymptotic, about how it falls back again the other way, that in some sense that is as of the accumulation and the acceleration and deceleration as either side. It's kind of like when we talk about this energy as a usual concept, that what's conserved in physics, the quantity, it's energy. And then with regards to all its transitions and states and coming and going from each of these transitions and states, then shows that while that is built up to that common milieu, it has to be taken back down from that to help explain these more of the theory of some potentials that go into all the theory to make for what Einstein calls his attack on Newton's laws, after his defense of Newton's laws and Einstein's laws for motion and classical motion, then with regards to the moment as basically the axis of change, or the moment as regards to the instant, and these kinds of things. And here, as has been discussed in these notions of transforms, when we have a picture of a time over time with regards to how these transforms basically build and combine to then have in their center their fixed points as about their singular points and their projections and perspective, all the way coming back to these kinds of things. So it's kind of relevant and interesting to get into this. The subject of singular integrals has undergone a considerable development in the last 20 years as a result of the works of Milan, Calderon, and Zygmund. So Zygmund will probably be the most familiar name of those. It sticks out, Zygmund. It's kind of unique. It is shown to have important connections with the study of Fourier series, Fourier. It's funny, you'd think it's pronounced Fourier if you were English and American, but then you hear it's French, and so you think it's pronounced Fourier. Well, it might sound like that, but then you read somewhere it's pronounced Fourier, or something like that, and kind of in the middle, Fourier. Partial differential equations and other branches of analysis. And he says that the classical example is given by the Hilbert transform, 1 over pi integral from negative infinity to infinity of f of t over x minus t dt. So here we have a couple things going on with that with respect to 1 over x, and here the identity dimension, x equals y, and then when we have t on the side of that, or with regards to that x minus t has that in the denominator of this term, it can never be 0. And so it kind of arrives at that there's for where this 0 is this usual singular point, and it's indispensable. It's part of the number system, and it reflects things about the envelope. It's almost always the trivial solution to partial differential equations, or differential equations, excuse me. 0 is central, and much that goes on about the symmetric and these other notions of the meromorphic about the thing. Free analysis on the plane, usually to begin, has that that's how it is. And so this identity dimension is really very similar in that for a lot of these simpler equations, like where the differential equation, which you usually would think is something that's kind of highly reflects a rapid change and then a rapid approach to then a slowing and a gradual approach. Smooth curves that are everywhere curvilinear also has that the lines through the origin are also differential equations in the setting, as per the linear fractional equation and being so parameterized. And so this identity dimension is kind of like 0. It sits in the middle of it, so it's singular and important, and ends up being that it's underexplored and underdeveloped with regards to otherwise that these become submersions and immersions of this differential geometry, I guess you might call it, that is with regards to how forms can be made sensible and fungible in these simpler cases, why it is so that what's of interest here is kind of the greater surrounds. So that's how I kind of want to frame just even this very simplest thing about how they all start getting staked out by these fixed points, and so it's kind of a key thing to look for the lesser explored to find the possibility for greater gain. Because then if the idea is that, well, if you can make it sensible and fungible to approach symmetries, submersions, and sheaves in descriptive differential dynamics and arrive at what's necessary for function theory and topology to make for this operator calculus, operator theory, all these kinds of things like addition formula and multiplication formula and exponent formula and convolutional formula and these other kinds of results after algebras and products and the closures, whether they have unbounded or unbounded closures of the finite or unbounded and infinite, or they have non-existing closures, or they even have these anti-inductive closures, that the idea is to fill it up with only about that much context, that's enough of the needful to make for all the tools that would reflect anything that's real and correct and accurate and perfect, free analysis on the geometric plane with regards to that. Otherwise the one-dimensional and the one-dimensional is just kind of a matter of magnitudes and reaches out and makes for this kind of fuller mathematical context that's still so absolutely connected to all the classical facts that are known and the mathematics that build it up together, and for making it so that it's a coherent universal language, and to identify where various subfields have kind of encroached on each other, what it is so necessary to tussle them apart or put them back together. Similarly, so for taking some of these approaches in the transforms and finding about these singular points and where they commingle in a sense, that there's what is this idea of, for example, the Claro-Maclaurin putting together Fourier and Taylor in regions as about what? Well, as about F0, or you know, that the Maclaurin is a trivial case of Taylor, and Claro is sort of a trivial case of Fourier. Then with the idea to arrive at then when it's so that these and this extension after zero, and then after getting into the identity dimension for various plane curves and isosivas, that's a new one, but gently these notions of these envelopes that are undefined but actually kind of define the area of these things, the space of these things, then it makes more of a spatial analysis in terms of these kinds of things. So it's not very well explored, it's not very well explained, and it's not very well understood. These kinds of approaches in the general setting, they're most always usually otherwise part of the grab bag toolkit of hard-learned applications, where it's found that what's so most necessary about them is to bridge this gap, bridge these chasms, overcome the inductive impasse of this meeting in the middle of nowhere, which is the usual subject of these talks. So it's higher mathematics, it's advanced mathematics in a sense. So what this gets into is just an example of that, looking at this here. I wanted to read some context now from Neri as he explains. Even if f is a very good function, this is that f of t over this quantity x minus t integrated by dt is the integrand of this Hilbert transform. The integral as it stands does not exist due to the singularity of the integrand at x equals t. However, following Cauchy, we may consider this integral in the principal value sense, PV, by removing a symmetric neighborhood of the singularity. Basically, then he has it from the left and from the right. This singular integral, or principal value integral, arose in the study of boundary values of analytic functions. So when you say analytic, we have a lot going on with regards to that. This is often this is always assumed to always also be so in the complex numbers. These values and this approach in Neri is vectorial and vectorial in the complex numbers, vis-a-vis univariate functions and real valued and scalar functions. There are approaches to break that down to make it less general than what he begins and continues to so develop in this course of these lecture notes, about how then the idea is to look and find in those how to build completions back out again, where it can be very fruitful in this sense for these approaches to combining the researches. So when he mentions that it says of the boundary values of the analytic functions, that gets into all these definitions of analyticity and the Gaussian Eulerian and all this kind of stuff here with regards to that. So he goes on to introduce convolution, and it's a pretty general approach. I'd kind of leafed through this first part already, and he gets into the l.t.e spaces are no more comparable. For example, f of x equals 1 over x. This is the hyperbola function, and it's symmetric about x equals y, and it is discussed quite thoroughly in consideration. Then also with regards to the hyperbolic functions cosh and sinh, e to the x plus e to the minus x, or 2, and so on, about what's being discussed here as with regards to those in the having and doubling in the 2x2 squaring and windowing and boxing with its x squared minus 1 stuff, about x squared plus minus 1. So he goes on to talk about Hoelder's inequality, and so after something like the triangle rule and triangle inequality, and then Cauchy-Schwarz inequality for the vectorial, and then up into the complex, and then Hoelder inequality, these are the very essential rules that make it so that they establish that then the bounds exist, and so something can be so well defined in that manner. He explains it as so. The norm of this f of p equals integral absolute value of p dx, that quantity, to the 1 over p satisfies the triangle inequality. So these Banach spaces, L to the p equals LP e to the n equals f of the integral from the absolute value f of x to the p dx less than infinity. And he has a typo, where, he's missing an e there, but where the functions f are measurable and complex valued in general, and two functions are identified if they coincide, almost everywhere, AE for almost everywhere. You'll find this almost everywhere, and it usually will indicate that according to measure theory, it's kind of so because a countable complement builds it up, and then you just say it's almost everywhere. Because otherwise you can kind of make a direct extension that says, well, can't reach the limit, because then it would, you'll have to make one. You have to make your own. And so this is basically its statement. The norm f of p equals this integral, absolute value f of p dx, satisfies the triangle inequality. The norm of f plus g of p is less than or equal to norm of f plus norm of g. So this is like this scalar product is always less than the sum of the scalars. That's the usual thing to think about it. Also, we have Hoelder's inequality. The integral of fg, their composition, dx, is less than or equal to fp gp. So the great key thing about these spaces, the functions in these spaces, is that they hold up this relation. So it's a relation, and then it becomes really relevant later when it's introduced after the transforms into the convolutional setting, that the convolution is like the integral of f of x and f of x minus y. Now, why is that going to be so great? Because when x equals y, both f of 0 makes it 0, and f of x equals y makes it 0. So in that particular parameterization, or the implicit, it's always as sort of so convoluted or convolutional. And so it'll make for a great sort of approach in this singular setting of the convolutional setting, which is a very valuable tool in the analysis after transforms, just about so how it helps to explain how to relate these things then to inverses, and where inverses do and don't exist. And it helps to explain some of the reasons why, when we're talking about Banach spaces, that it only exists for these values p between 1 inclusive and infinity, but not for less than 1, only between 1 and greater. So it's kind of out of this, so that 1 over p is always between 0 and 1, inclusive. That these orders of these are like so. And then the author deals pretty much with L1 and L2. If p equals 1, then Hoelder's inequality holds with p prime equals infinity. So that's the notation, and while it reflects one's quantity, then it means here the derivation of the quantity, as has been discussed here quite a bit. So this is kind of in the notion of the setting of descriptive differential dynamics, and what's carrying on from there, where we set the norm of g sub infinity equals the essential supremum of gx, the least number m greater than equal to O, such that gx greater than m only on a set of measures 0. And define the Banach space L to the infinity accordingly. We recall that the spaces LP and LP prime are dual, with a dual pairing, and here he's got in brackets f comma g equals the integral of fx gx dx. So this reflects on that in the identity dimension on that line. Then the convolutions are duals too, and there's later made use of that same kind of property with regards to those being related types of things, for associating these things pretty generally, and helping to relate arithmetic of addition and multiplication and exponents and the logarithmic and roots and powers, then into this convolutional setting about the integrals and about the orthogonal functions, and those being the basis for transforms. Then the convolutional setting that so follows, that up and after these quantities, that again this identity dimension is becoming more of an idea fix. So we recall that the spaces, if E is a subset of E sub n, one defines similarly that spaces LP of E for these spaces above facts also hold that the absolute value of E denote the measure of E. If measure of E is less than infinity, we can modify the definition of norm in LPE by considering the average. And he says the average of P bracket F equals this quantity, 1 over the measure of E of the times the integral of E to the measure of F to the P, all that to the 1 over P. So, and this is in a sense, it's kind of defining it like the geometric mean. What's the arithmetic mean? Take the sum and divide it by the count. What's the geometric mean? Take the product and take the root of the count. So here it's similar. And that gets into stuff like the isoparametric theorem that was discussed, and the arithmetic and geometric and harmonic means, about the ideas when those meet, and about the 0.25 and these kinds of things that came up a lot in the 2x2 boxes, and these kinds of things that go on, and as to why it's kind of funny that pi is less than 4, e is less than 4, root 2 is less than 4, phi is less than 4. So the idea of that all these kind of constants kind of build up and out pretty surely, certainly out of 0, 1, and infinity, that 0, 1, 2, and then this stuff that comes up around it, about the things like the root 2 over 2 plus root 2 plus root 2 over 2 plus root 2 plus root 2 over 2. And there's relations to E and pi, and these various infinite series that make them like so of arithmetic, that it's amusing me quite a bit to start building this up and bracketing it out and boxing it and windowing it in a 2x2 square, and helping relate how then it's possible to put at least some things in that kind of setting, which helps makes for some of these analytical results then, with the idea of trying to work up what are some usual, simple, and sensible things, and as with regards also to their digital approximations, so that then it just results that also you can just declare it as an array and have a superscalar approach on the computer step through it, making stuff crunchable, making stuff tractable, formable, sensible, fungible, and tractable. These are the kinds of ideas that would definitely be of some sort of analytical interest, besides that there's very much fundamental interest in it. So I'm glad I've been reading these books. So when he gets up to it, then he talks about the converse of Hoelder's inequality. If p is greater than 1 and 1 over p plus 1 over p prime equals 1, then the integral of fg dx is less than or equal to fp for all g with g of p prime equals 1. So we are often looking for stuff that equals 0, the additive identity and multiplicative annihilator, or 1, that the multiplicative identity and also for division, that then it results that it algebraically falls out of these quantities, so connected, their product terms, they're derived. So these are then their fixed points. They're singular points and fixed points. So what he does is he defines convolution. For let f and g be measurable functions of x in e to the n, we may assume for simplicity that f and g are real valued. The convolution, h equals f star g, it's usually written star. The asterisk is often written as multiplication, or x is written for multiplication, but x is also written for the cross product. All over mathematics, of course, terms are just written in a row and they're multiplied together because the variables have single letter names. So the product term is not overloaded, it's just implicit. So here convolution is star. H equals f star g is defined by h of x equals f star g of x equals the integral f of y g of x minus y dy. So this is then about the convolutional setting, about a function that's convoluted to itself. F star f is one thing, where when f of 0 equals 0, or that otherwise that the identity dimension is kind of it's a line through it, is that that would also be g of 0. So always one or the other of those terms will be 0 on that line. So the integral of that integral of dy, where integration is over the whole space, and integral is the Lebesgue integral. So Banach 1, or L1, is not closed under pointwise multiplication. Convolution is a kind of multiplication. For instance, f of x equals g of x equals x to the negative 1/2, or 1 over x squared, belongs to L1, 0, 1, but fx gx equals 1 over x does not. However, L1 is closed under the convolution product, as the following theorem shows. So this is helping establish them, try and figure out an interpolation among these spaces, and where the product settings of terms exist, that is exactly the sort of things where it's not defined that really builds up a lot about its grounds. It's pretty cool, I think. Theorem 1, if fg are in L1, then h equals f star g exists almost everywhere and belongs to L1, that the results of this operation are closed in this space and exist in this space. Also, the norm of h sub 1 equals their norms, is less than or equal to their product norms. Proof. The length length of hx is less than equal to the integral of the length of fy times the length of g x minus y dy. Integrating an x and interchanging the order of integration, Tonelli's theorem, since g of x minus y is a measurable function of x comma y. So he says Tonelli's theorem, the integral that h of x interchanged dx is less than equal to the integral of dx, this quantity, integral of fy g of x minus y dy equals integral of fy dy, integral of fy interchange dy of this quantity, integral of measure g x minus y interchange dx equals norm f1 norm g1 is less than infinity. Hence h of x is less than infinity almost everywhere, and the norm of h1 is less than equal to f1 g1 qad. Now I've just read that off, and I don't really have a very deep understanding of it, because I'd have to really look into what's going on with Tonelli's theorem and this interchange about the order of these two terms with respect to each other in terms of the scalar, the univariate, the real valued, in terms of the symmetries and the reflections and the notions of these two sorts of functions, one in their difference terms with respect to each other, and that otherwise it's from left to right, f to g is f of y and g of x minus y. But it could, because what he says is next is one of the great things, convolution is commutative. That means it goes both ways. That is f star g equals g star f. But the difference term is in this one way or the other way. So it's kind of one of these things, kind of like when there was discussion of the complex analysis after the identity dimension. There's only occupied 1/4 of one quadrant for this only positive terms. So usually then you just fill out the rest of the plane because there's negative terms. And then usually you just fill out all over that, you make a complex diagram over the whole thing because there's complex roots and complex terms. So instead, you just have this upper quadrant, and then you just kind of fold out to the left or the right, left-hand side and right-hand side of what is this complex division, which is defined to be commutative when it could really be not, because you could set it up to be uncommutative. And so in this matter, then it's possible to sort of make it so that one can imagine how a similar notion to convolution could be this complex convolution, how it so arrives at an idea. It's not very well explored, but due to the fact that it just exists as an object of mathematics is some kind of new mathematics that somebody probably already knows about and is written up and it's in the academic creed and the canon and all this kind of stuff. In the stacks, that this is the kind of idea from reading these definitions, how to help it be associated with otherwise these developments in these deconstructive accounts that are making for why this is sort of a rich way to approach a second course in descriptive differential dynamics to help better digest the first one. Convolution is commutative. In fact, f star g of x equals the integral of fy gx minus y dy equals changing variable z equals x minus y dz equals dy. So z here would be, in the identity line, it would be 0, and dz equals dy would be 1. Equals f of integral, equals the integral of f of x minus z gz dz equals g star f of x. So then that gets also that the identity dimension is like x equals y. It's also like x equals y equals z. It's also like x equals y equals z equals next. It's also like not those. So all the abscissae and ordinates. So connect them and drop them for the tangents and the subtangents. These being the traditional terms that are gathering some dust because they, although perfectly apt and related directly to geometric, are just a little bit off to the corner in the grab bag toolkit of all the analytical methods of mathematics. So yeah, so today's talk, I really want to just get in convolution a little bit and introduce it as a concept. And after there was the mathematics of medical imaging, then there was arrived at something like this deconstructive account that helps make for why it's sort of a way to help enrich the understanding of it because it's full. And so these are the kinds of things. Exercise. Show that in L1 convolution is associative. That is, f star g quantity star h equals f star quantity g star h. Hint. May assume fgh all greater than equal to 0. Interchange the order of integration and use an appropriate change of variable. Remark. There is no function g such that f star g equals f. However, the Dirac measure delta, and I really enjoy this description because it's quite non-standard, and by its assertion, though, it sort of says it has to exist. However, the Dirac measure delta, which assigns mass positive infinity at the origin and mass 0 elsewhere, satisfies f star delta equals f in the sense of distributions. So delta is an identity. When I read that, I had already read this before, and so when I read this remark, that today it's the Dirac delta is everywhere, and I mean it's the only non-standard function, in use in a lot of different senses. That it helps explain that in its role in these numbers is like this is an identity. Now, what if there are others? It doesn't say the identity is unique. We know that our usual notion of groups is that there is an identity. X plus 0 equals x. X times 1 equals x. There's a unique identity in these structures. It's not necessarily so. The properties of the associative and commutative and the transitive are key in defining things like the operations of fields and all such matters of the operator calculus that establish all these sorts of things. Theorem 2, courtesy, W.H. Young. Let p between 1 and infinity. He's got inclusive ors now in both of those. Before he had 1 less than equal to p less than infinity. Now the author's written 1 less than equal to p less than equal to infinity. Is that on purpose? I don't know why not. If f is an element of LP and g is an element of L, then h equals f star g exists almost everywhere and belongs to LP. In fact, norm HP is less than equal to norm FP, norm G1. So this is interesting because instead of having them in the same order and rank, it's kind of like dealing with this scalar term. With regards to like a vector field, and linear algebra is a great facility with usual coordinates and just plain old vectors, x, y, z, and E1, E2, E3, the orthonormal vector bases, and the properties of a vector field, that it has an identity, and that any vector can be summed with another vector, and any vector can be multiplied by a scalar. And it satisfies this same rule. Proof. The case p equals 1 was proved in theorem 1. If p equals infinity, let m equals essential supremum, fx equals magnitude of f infinity. Then for almost every x, magnitude of hx less than equal to the, instead of the convolution product, that it's just got the absolute values inside that. So before the convolutional product was like the integral of fx g x, or f of y g x minus y dy. This is the measure or value of fy, and that also of g of x minus y dy. Also less than equal to m times this g of x minus y dy, where that equals this norm f infinity g1, which implies a conclusion. So this is just pretty great because what it does is it helps build up and build out that usual singular points like 0, 1, and all falling back down to that is here's like, well, here it's just kind of framed in terms of 1 up to infinity and all the way up into that. How it is this kind of symmetry and reflection. Kind of like the inversion of a point in a circle is you take a circle. And so any point within that circle, you draw it out that measure, and then you reflect it outside. This is the inversion of a point about a circle. So the one at 0 is an infinitely sized circle all the way outside it. It's a singular point. Every singularity is a multiplicity. We're used to dealing with the principal branches of things. Keeping things simple. It has all the rest. Keeping things simple. So anyways, this is something that I would look to these notes again and find that there's much value in them. And that I was going to learn a lot about the inversion. He talks about an inversion formula. We seek a representation of fx by means of its Fourier transform. And he writes inversion formula. However, f hat need not be integrable, so the integral is not convergent in general. For this reason, we introduce now the concept of summability of integrals. And then he introduces this notion of the partial integral. This is a great development, a great grammatical toolkits in Neri's works here in singular integrals. Basically go with symmetries, submersions, and sheaves. Singular integrals. I got a couple other volumes in this series. One is the Symposium on the Theory of Numerical Analysis. So numerical analysis has come a long ways because since this time, like 1960, the computers have become available to do a lot of this kind of computation. It's got stuff from Golub and what is this? Yeah, I was kind of interested in this. Golub, direct methods for solving elliptic difference equations. Golub, matrix methods in mathematical programming. Tomei is pretty famous. Topics and stability theory for partial difference operators. Walkspress, iteration parameters and the numerical solution of elliptic problems. Wildland, introduction to finite difference approximations to initial value problems for partial differential equations. So this is a great little book. It's got a lot going on it. It builds up its formalisms. It's got a bunch of stuff scribbled in it. They kind of ran out of typeset at the time, but this is how they've made it so. Copies. General Electric Company, Schenectady, New York. So you might say, wow, that sounds pretty interesting about algebraic geometry, Grothendieck universes, Shimura Taniyama, and the conjectures about Fermat's last theorem, and suggestions of solutions about elliptical equations, and these kinds of things, and the Galois fields, and GF2, and these kinds of things. Yeah, it kind of does. Geometric aspects of the Einstein equations and integrable systems. So this says it's proceedings from Scheveningen, the Netherlands, in 1984. So this is issue 239. I just kind of picked these up. There are oftentimes I got it from people who are retired mathematical interested engineers, who read these books that they bought. The present volume contains the notes of lectures delivered at the 6th Scheveningen Conference. So for Einstein, it says Einstein equations, so usually you'd think it'd be the Einstein field equations for the gravitational field equations. So these basically reflect a covariant or coordinate-free setting between the metrics, various Euclidean matrix and Riemann metrics, are basically the holes that you think of like gravity is like it's like a sheet with weights on it. So when something rolls along it, it'll just kind of roll into the dips and the valleys and all this kinds of stuff. Or you can look at it and say it's flat, and then anywhere there's gravity, it just makes a well, so it falls in and then it falls in. This kind of thing. Fall gravity is according to these gravitational field equations. And then how those are put together, it's like, well, I don't say how they're, Einstein doesn't say how they're put together, he just says they must fit. So this book has a bunch of stuff that's pretty cool. Exact solutions in gauge theory, general relativity, and their supersymmetric extensions. Oh, this sounds amazing. Xanthopoulos, symmetries and solutions of the Einstein equations. Xanthopoulos, superposition of solutions in general relativity. Bauerl, gauge fields, gravitation, includes the Klein theory. So these days it's pretty well understood that physics is unified. It's called the unified field theory because it's unified forces, and all the fields and the forces live in one field, and it lives on a continuous manifold called space-time. And so arbitrarily enough, general relativity on the one side and quantum mechanics on the other side all fit in it. And so the idea then for the highly nonlinear, highly nonlinear, and asymptotic, that's gauge. And so with regards to being a field theory, it's a gauge theory. And the usual idea is that the gauge everywhere is pretty normal, and it is continuous. And then with regards to torsion and twist, this is like, I would probably look to Rindler, that Rindler has about the most going on with respect to these changes in the coordinate settings, what result, how, and why, that it's a gauge theory and such. Dre, gravitational shock waves. Sims, soliton surfaces and their applications. Soliton geometry from spectral problems. So these are quite advanced and high level concepts about things like the induced metric, local coordinates, Killing-Cartan of Lie algebra, soliton manifold, soliton field, reduced Gauss-Maynardi-Kodachny-Ricci equations. Because as we get up into the Ricci tensor, that's one of the most kind of flexible adaptations of in the covariant analysis and the coordinate-free analysis as with regards to how those things keep together. About Bianchi-Backlund, that Backlund geometry is a great thing after the Bianchi identities. Of course, a positive answer to these questions provides us with, for example, a spectral meaning of the Bianchi-Backlund geometry, or a generalization of the Bianchi-Backlund mapping, etc. The above questions seem rather difficult, and it is surprising that the positive answer to the above question is relatively simple. Completely integrable systems of evolution equations by Duge. Nijhoff, Kappel, and Wiersma, integrable lattice systems in 2 and 3 dimensions. Facquerel, isovectors and prolongation structures by Vessiot's vector field. Van Grossen, Hamiltonian flow on an energy surface 250 years after the Euler-Maupertuis principle. So Maupertuis is real important. Maupertuis is really pretty great. So I'll be curious to see what that says. Norma Sanchez, Department de Astrophysique Fondamentale, Francais. We analyze the nonlinear and topological structure of gauge theories, sigma models, and general relativity, exhibit their solutions, vortices, monopoles, instantons, calorons, plane waves, singularities. Investigate their interconnections, self-dual and non-self-duals, with and without Keeling vectors, present for the subclass of theories which are known integrable, their integrability properties, lax pair, infinite number of conservation laws, infinite dimensional Lie algebra of dynamical symmetry transformations, Becklin transformations. We review their supersymmetric extensions, supersymmetric, non-abelian Higgs model, sigma model, Yang-Mills, gravity includes a Klein. That's ambitious. Hamiltonian flow on an energy surface 240 years after the Euler-Maupertuis principle. This paper is concerned with one of the basic formulations of the laws of classical and modern physics, viz. The principle of least action. It is. So we've been talking here about the principle of least action. It's got a lot going on with regards to that the principle of least action has a counterpoint. And it's the emergence of information and what it means for this idea of like the free information is one of these concepts that was part of one of these other earlier moment and motion talks. And another one is with regards to entropy and entropy. And with regards to it, it's kind of its own dual, being as for itself what it means and that kind of thing. That this amuses me. This introduction thus far, what he's going to say. Generally speaking, this variational principle determines the actual motions of a Hamiltonian system at a given value of the energy by the property that they correspond to the critical points of the action functional, which is a functional defined on curves and configuration space. Short historical review of this principle, which is generally named after Maupertuis, but should be called more correctly the Euler-Maupertuis principle, is presented in section 2. It's a pretty ancient principle vis-a-vis this statement here. He wants to give a new, simpler formation. So he just says he's working on a setting in his configuration space that he's doing a rank reduction about a functional, and then if he gets into Hamilton-Jacobi, today it's called Hamilton-Jacobi equation instead of just Hamiltonians. So I wonder if this is related to that. Note the difference with the usual Jacobi functional, which can be written as ... So this is kind of in the time when that was coming up. So it's not really, that's kind of bringing together when there's multiple fields interacting and helping to make them in accords with regards to, as so necessary, making it the theory of some potentials and this kind of thing. But otherwise, this is very great. Euler describes the basic idea of the principle as follows. And excuse me, I don't speak German or French. Okay. Dan nämlich die Körper wegen ihrer Tragheit jeder anderen ihres Zustandes widerstreben, werden sie den inverkehenden Kräften so wenig wie möglich nachgeben, wenigstens wenn sie frei beweglich sind. Daraus folgt, dass die wirklich bewegen, die Wirkung, die durch die Kräfte hervorgerufen wird, kleiner sein muss als für irgendeine andere Bewegung, die man dem oder den Körpern auftragen könnte. So he's kind of describing that really that they items, the bodies in their work minimize this. A few months after Euler had written these lines, Maupertuis, 1744, presented a paper to the Paris Academy entitled Accord des différentes lois de la nature qui avaient jusqu'ici paru incompatibles. So, laws that were at odds or incompatible after a deconstructive account put back together, or maybe just left apart. In this paper, he presents, independent from Euler, a principle of least action. In his words, le chemin est celui par lequel la quantité d'action est la moindre. The quantity of action is least. With Fermat's principle of least time, from which he establishes Snell's law as the only specific example in the paper, he mainly founds his principle on metaphysical laws, such as la nature dans la production de ses effets agit toujours par les moyens les plus simples, and la nature dans la production de ses effets agit toujours par les voies les plus simples. So towards the means and towards the voies simplest. Although, chronologically speaking, Euler has the priority, we can point back about 2,000 years. The ancient Greeks already have this kind of law. Nevertheless, Euler strongly believed in the validity of the principle. Zweifel liegt nicht, dass es möglich sein wird, ihn mit Hilfe einer gesunden Metaphysik besser zu begründen. And in a letter Maupertuis J'estime le développement de cette matière equals the related principle of minimal potential energy. So potential energy is our idea here. Infiniment plus que les solutions les plus recherchées des problèmes particuliers. En effet, je suis convaincu que partout la nature agit selon quelques principes d'un maximum ou minimum. This short historical review, initiated by reading the intriguing remarks of Goldstein, 1980, on this subject, may suffice to justify the name Euler-Mapuche principle to the principle of least action, and at least when considered as a variational problem for a functional which is defined on curves in configuration space. ... in a theory of some potentials. So you can add that bit later. Well, all right. Hey, have a great day. I shall so hope it's a good day.